Okay, let's get started. So today we've got a few things to go through. So I've got 10 problems on finding the domain of a function. A little bit more difficult than what we covered yesterday. So 5 of them we're going to do in class. The other 5 I'm going to leave for homework for you to try out. Then we're going to finish off that proof on the unique decomposition of a function into even and odd parts. So the first part we did in class, the second part I left for homework. Did anyone figure it out? The second part? You got it? You think so? Okay, that's very good. Anyone else? Okay, 2, 3, okay, a few. That's good. So we'll go through it, see if it matches up. Remember, it doesn't have to be exact, right? There's different ways of proving things, but if it's right, it's right. Okay, so you can have a look. And then the last thing for today is injective and surjective functions. Okay, we're going to need that for next week when we do inverse functions. Okay, so let's go through these 5 first. And again, the other 5 that will be for homework. So we want to find the domain of these functions. So we've got our first one here. It's a rational function. Okay, remember from the list of elementary functions. So we have a polynomial at the top, polynomial at the bottom. That makes it a rational function. Okay, so we want the largest possible domain, which is a subset of the real numbers, where the function is defined. So we start off with the domain. Let's call it x, like we did last time. So it's going to be all of the real numbers, because we want to do calculus over the real number line. But we can't have all of the real numbers, right? There's those problem points that might come up. So it's all of the real numbers minus any problem points. Okay, in this case, we have 1 point that causes us issues, and that's where that denominator there is 0, right? If you divide by 0, it's problems, which means the function is not defined there, so we need to remove it from the domain. So that bottom part is 0 when 4x minus 9 is equal to 0. So we can do a little side calculation if you need to. So 4x minus 9 is 0. 4x is 9. X is 9 over 4. Okay, so we know where the problem is. It's at this point over here. So if we take the whole real number line and we remove this point, we're going to have 2 parts. We're going to have one part from minus infinity up to this point, not including this point because we took it away. And then we're going to have everything from this point up to infinity, again, not including this point because we want to take it away. So this is going to be all the real numbers from minus infinity up to this point that we want to remove. Union, and then all of the numbers after the point that we remove. Okay, and that's our domain. So it's everything except this point over here because the function is clearly not defined there. Any questions for this first problem? Pretty straightforward. Okay, let's look at problem number 2. So here we have f of x is equal to 2x over x squared minus 4. Again, it's another example of a rational function. We're going to see lots of these coming up. Okay, so just get used to the terminology we use, right? Rational functions, polynomials, exponentials. You should know all of these words from yesterday. So again, it's a rational function, which means we have issues when that bottom part is 0. That's our problem points. So a little quick side calculation. Let's see where this is 0, and then we're going to have to take those points out. So on the side, we have x squared minus 4 is equal to 0. We can factor this as x plus 2, x minus 2. So here we have 2 problem points, one at minus 2 and one at 2. So both points need to be removed. So minus 2 and, we can put there plus 2. So minus 2 plus 2, that needs to be taken out. So if we take the whole real number line and remove 2 points, we are going to have 3 parts to the domain. we're going to have everything from minus infinity up to minus 2, not including 2. We took it out. Everything between the 2 points from minus 2 to 2, and everything after 2. Okay, so we took 2 points out, so we have 3 parts to the domain. So let's write them out. So everything from minus infinity up to this first point. Round bracket, not including the point because we're trying to take it away. Everything between these 2 points. And finally, everything after that second point. Okay, so we have 3 parts to this domain, where there's a point removed over here by this union, the minus 2 is removed, and over here the plus 2 is removed. Okay, now there's a very common mistake that I've seen over the years with this, is that students find the point minus 2 and plus 2. They write this part, because it goes up to minus 2, they write this part from 2, and they ignore the middle part. Okay. So please put a big warning there. Make sure that you include this middle part as well. Don't just think it's the domain up to minus 2 and the domain from 2. This middle part needs to be included. Okay. A lot of times this middle part is excluded. So please just keep that in mind. Okay. Pretty common mistake I've seen in the tests. All right. Any questions for this one? Okay, pretty straightforward. 2 points to remove, and then you get that union over there. Okay, number 3. Here we have f of x is equal to x squared plus 2x plus 1 divided by x squared minus 8x plus 12. Okay, again, rational function. Please start using this terminology. So we have a rational function. We want to find the domain. We know right away that the problem points are where this bottom part here is 0. We want to take those points out. So we do a little side calculation. Where is that bottom part 0? So x squared minus 8x plus 12 is 0. And remember, a couple of days ago, I've really emphasized your algebra, factoring polynomials, finding the roots, all of that stuff, completing the square. It's all in these side calculations that you have to do. So here we've got polynomial equal to 0. We need to find the roots, right? That means we need to factor it. If you can't do the side calculation, well, now you can't do the main question that I ask. Okay, so it's very important that you can do this algebra here. Okay, so we want to factor it. What are the roots? Oh, what is it? 6 and 2. Good. So we got 2 and 6. That's going to cause us problems. So same as before, when we had the minus 2 and 2, everything is fine up to 2. 2, there's a problem. Between 2 and 6, everything's fine. At 6, there's a problem. After 6, everything's fine. So we need to remove 2 and we need to remove 6. So everything up to 2, everything's fine. Round bracket, we want to remove the 2. Union. Between the 2, there's no issue. Again, round bracket, we want to remove it. And everything after 6, there's no issue. So we can go union 6 to infinity. Okay. And that's our domain. Again, 2 and 6, those are removed. And like in the previous one, make sure you include this middle part as well. Okay. Otherwise, 0 for everything. Okay. Any questions for this one? Okay. Pretty straightforward. So the general idea for rational functions, like we've been working with, you look at the denominator, you set it equal to 0. That gives you your problem points. and make sure you remove those. Okay, so that's the process for a rational function. Number 4, here we have something slightly different. Here we have 1 over root x minus 1. Okay, this is not a rational function. The bottom part is not a polynomial. Okay, so it's not a rational function, but the idea is the same. Because we have 1 over something, that bottom part cannot be 0. Otherwise, you're dividing by 0. So that's the first thing. That bottom part cannot be 0. But we also have the root to deal with. Because we have the root, whatever's inside the root must be positive, right? So there's 2 things we need to think about. Firstly, we're dividing by this whole thing, so it can't be 0. Second, this inside part better be positive. Okay, there's 2 things to worry about. So let's focus on that inside part being positive. So we want x minus 1 to be greater than or equal to 0. Okay, so for the first part, root of something inside must be positive. So x minus 1 better be greater than or equal to 0 for this to work. So x is greater than or equal to 1. So if x is greater than or equal to 1, this inside part is positive and we can take the root. But the second thing is we cannot divide by 0. What number or numbers makes that bottom part 0? 1. In this first part, we could include 1 because it still remains positive, but the second part said, no, we must remove 1. So it's not going to be greater than or equal to 1 because this says we must remove 1. So it's everything strictly larger than 1. Okay, we cannot include 1 because of the second part here. So the domain will be everything after 1. Round brackets 1 to infinity. Okay. Does everyone see what we did there for this 1 and 2? Okay. So the first part, the root must be positive, that inside part, so greater than or equal to 1. However, it can't be equal to 1 because then we're dividing by 0. So it needs to be round brackets on the 1. Okay. So it must be this bit and that bit. Okay. Any questions for this part? All clear. Okay. So we're going to do 1 more in class, and then I've got 5 for homework. Okay, we've got log base 2 of x minus 1. Again, logarithm, it's an elementary function. Right, please get used to these different functions. So this inside part here, there's a restriction for it. Okay, if you look at the graph, there's a restriction there. What values over here can we substitute? If you have a look at the log graph, can you put negative values? No. Can you put 0? No. Anything after 0? Yeah, that's fine. So this inside part must be greater than 0, not equal to 0. Again, if you don't see that, look at the graph. So it looks something like that. We've got this asymptote, right, at 0, so we can't put 0. Over here, there's no graph, so that's not part of the domain. But everything on this right side, that's fine. Okay, so we want x minus 1 to be greater than 0, not equal to. We can't have that. We just take the 1 over to the other side. Okay, so that's our condition. X must be greater than 1. So we can write out the domain. So we can have a round bracket at 1 because we're not including it. And then anything up to infinity, that's fine. Okay, and then round bracket as well. Okay. Any questions for this one? All good. Okay, then the homework problems for you to try. So this will be 6 to 10. So number 6, we have f of x is equal to root x plus 3 over x minus 2. Okay. Notice the top we have a root, so that's going to cause some issues. And in the bottom, we can't divide by 0, so that's going to be some issues there as well. Okay, so 2 things to consider for number 6. Number 7, we have the root of x squared minus 2x minus 8. Okay, here we have a root, so this inside part cannot be negative. Okay, so just keep that in mind. Number 8. We've got another root here. Right, that inside part can't be negative, so check for that. Number 9. F of x equals 2 times x to the 3 over 2. And again, just for the terminology, what type of function is this? X to something is a power function. Okay, again, please get used to these names. Okay, so there's a power function. We have some real number times x to some real number. It's a power function. Okay, and then number 10. Okay, so we have sine of 1 over x. Okay, so the sine function, that's not going to cause us any issues, right? It's just the sinusoidal, which here there's some issues there. All right. Any questions about the homework problems? Okay, so please try that out. Good practice for the quiz. Remember, the MCQ part of the quiz will include finding the domains of functions. So I'll give you a function, and then option A, B, C, D, you need to pick the correct domain. It'll be something like these homework problems and something like we did earlier. Any questions before we move on? Everyone's okay with finding the domain? Okay, let's move on. So yesterday we did the even and odd decomposition. So we proved the first part of the theorem to say that it could be decomposed. And then the second part of the theorem, the fact that it's unique, I left that for homework. Okay, so let's finish that up. So we want to show that the decomposition is unique. Okay. So I gave you a clue for how to do this. So we start off with 2 decompositions. We had the one with F and the one with G. We assume that we have 2 of them. So let's say number 1 is the one with F from what we had last time. So that was f of x is f even plus f odd. Okay, so I label that number 1. That is one decomposition. Now, I said assume we have another one. So f of x is equal to, let's say, g. So here we have 2 decompositions. And the goal is to show that this is unique. In other words, we want to show that these 2 are the same. Okay, so what can we do? Well, for equation 1, it's equal to f of x. Equation 2 is also equal to f of x. So if the left sides are equal, the right sides are also equal. So that side with the f must be equal to that other side with the g. Yeah. And that's where I ended the hints for you. Okay, so what we do, we're going to take all of the even terms to one side, and we're going to take all of the odd terms to one side. Yeah, and then on the other side, we have the odd terms. Okay. And then I said that we're going to use the definitions for even and odd. So we know that this is even, and we know that this is even. So if we substitute minus x into both of these, we just get back the original function. So from here and here, these are both even. The difference is also even. Because you put in minus x, and we just get back to where we started. Everyone clear on that? Yeah. So f even minus g even is even. Right? Like I said, you put in the minus x, and you just get back to where you started. That means it's even. Now this side, this is odd. If I put in a minus x here and a minus x here, I just get minus of the result. So this minus this is odd. Yeah, if you don't believe me, you check on the side. You put in the minus, you'll see it's odd. Okay, so what we have is this left-hand side is even. And the right-hand side is odd. Okay, there is only one way for a function to be even and odd. When will that be the case? There's only one way for the left-hand side to be even and the right-hand side to be odd. What case is that? Okay, think about it. What does it mean to be even? What does it mean to be odd? How can it be both? Okay, think about it for a little bit. Okay, how about to encourage you to think a bit? First one to get the answer gets 5 marks for the next quiz for free. Ah, who said that? 0. Well done. Let me get your student number. There you get extra 5. Yeah, right, to be 0. Well done. So 5 out of the 10, 50% for free. Well done. Okay. Yeah, so it must be 0. So this equation over here must be equal to 0. Those of you who didn't get it, think about it for a little bit, and you should see it. Okay, so we have f even minus g even is equal to g odd minus f odd. And like he said, this can only happen if it is 0. Okay. Now what we have is this part is equal to 0, and this part is equal to 0. So we can get 2 equations from there. Right. And we get this equation. Remember yesterday I said this is what you wanted to show. And then from this part equaling 0, we get another equation. A little bit of rearranging. And we're done. Okay. So like we had before here, if we just go back to lecture 4. There. This is unique if, very emphasized, we can show this. That was the goal for the homework, to show this. And now we went through all the calculation and we showed that. So it must be unique. Okay, end of proof. So now you have both parts of the proof now. Right. Any questions for this last bit here? Showing that they're equal? You're all clear. Okay, if you're a bit iffy still on proofs, please have a look at the YouTube channel listing that I put up for Michael Penn Math. Okay, it's in the list there. Just make a note. He's got a whole lecture series on proof techniques. Okay, so from right at the beginning when we did the set proofs and the logic proofs and these proofs, he covers all of that. Okay, Michael Penn Math, just check in that listing. Okay, if you're still a bit uneasy with the proofs. Remember, for the class tests and the June tests and the final exam, up to 30% of the assessment will be proof-based, seen and unseen. So you need to know how to prove things. So 30% proof, seen and unseen, and then 70% just calculations. You know, like find the domain, and you do the calculation. Okay, so 70% calculation, 30% seen, unseen proofs. Right. Any questions on this before we move on? All good. Okay, so please just add this to what we did yesterday so you have the complete proof, just in case it comes up. Okay, anything before we move on? All good. Okay. Next bit, injective and surjective functions. So quite a lot of definitions and terminology coming, so please be patient. This will be heavily used next week when we look at inverse functions. Okay, so we're just going to go through the terminology. We'll go through a couple of examples, but it will be mainly used next week for inverse functions. Okay, so what is an injective function? We'll do that one first, and then we'll look at surjective functions. Okay. So definition, an injective function. An injective function, also called a one-to-one function. That's another name for this. Okay. Maps one input from the domain to one output in the codomain. Good. Okay, so please get used to all these words that we're adding, right? Domain, codomain, injective, surjective, power function, rational function. Yeah, you need to be familiar with all of these. So one input from the domain to one input in the codomain. Okay, so we'll see some examples. So it must be one-to-one. Okay, so that is different from many-to-one. Okay, so many-to-one is not injective, one-to-one, that is injective. And we'll see some examples now. Okay, so let's have a look at two pictures, one that is injective, one that isn't, and then I'll show you how we check for this mathematically. Okay, so the first one, we've got the graph of y equals x squared. Okay, this is not injective. This is actually 2-to-1. And we can see that just by an example. Here we got -1. Here we got 1. Just two examples from two elements from the domain. Where does -1 go to? minus 1 from the domain goes to what's in the codomain? 1, yeah, 1. Where does 1 go to? 1. They both go to 1. We have 2 to 1. 2 elements go to 1 element in the codomain. This is not injective, right? It doesn't satisfy the definition. This is 2 to 1. Right? X and minus x both go to x squared. So it's not 1 to 1. It's 2 to 1. Not injective. We'll look at a similar example for this one, x cubed, and we'll do minus 1 and 1. Where does minus 1 go to? Minus 1 goes to minus 1. And 1 goes to 1. Well, those are different. 1 element here goes to 1 element here. Then, in contrast to this one, 2 elements here go to the same element there. So if you draw that horizontal line like we did there, it cuts 2 of them. It's 2 to 1. Over here, you draw a horizontal line. It only cuts 1. So it's 1 to 1. This is injective. Okay, and just as another non-example, maybe we do something like this. Right, we still have that horizontal line again. So we're looking at that particular y value. We see that there is this x goes to here. This x goes to the same y value. And this x also goes to the same y value. We have 3 to 1, not injective. Does everyone see that? So over here, this is 3 to 1. So 3 x values give us the same y value. It is not injective. Yeah. Everyone clear on the pictures? How to check? Okay, so this is just looking at the pictures to see how we can check that. Mathematically, if we want to show something is injective, we can do a calculation to show it as well. So here, if you can't draw the picture, then you have to do the calculation. Okay, and it goes like this. So if f of a is equal to f of b, so 2 y values are the same, then a must be equal to b. It must be the same point going to the same y value. Yeah. This is another way of phrasing the statement f is injective. So we do this calculation. So we start here. If we get to here, it is injective. If we don't get to here, it is not injective. Yeah, and again, 1 point, so a equals b, that means it's the same point, goes to the same y value. F of a equals f of b, so the y value is the same. So 1 to 1. Okay, so let's do this calculation for these two here. So we'll do it for x squared and we'll do it for x cubed. Okay, so number 1. So we have f from the real numbers to the real numbers. X gets mapped to x squared. Okay, again, just to give you the full notation for the function. Later on, we'll drop this because we will only work over the real numbers. But for now, we're going to put it in explicitly. Okay, so the idea is to show that this is not injective. So let's take f of a equals f of b and show that we do not get a equals b. So we take a and b from the domain, elements of real numbers, and we let f of a equals f of b. What we want to show is this part here does not give us a equals b, because it's not injective. This cannot be true. Okay, so f of a will be a squared. F of b, that will be b squared. Now, please do not fall in the trap of putting the root on both sides. Okay, you're going to make some problems there. Instead, we're going to take everything over to one side and then factor. Here we get two answers, not one. Remember, we should have gotten one for 1 to 1. Here we got 2. This, in case of our parabola, is the plus x solution and the minus x solution, right? We have plus 1 and minus 1. Okay. These are the plus and the minus that show it's not injective. Now we can do the same thing for the cubic example, and in that case we will get a equals b. Okay, so we got from real numbers to real numbers, x gets mapped to x cubed, and we follow the same procedure. So we have a and b from the domain, we let f of a equals f of b, and show that a equals b. Okay, so this will be a cubed equals b cubed. Now, what you could do is take everything over to one side, factor it, all of that. But we know we can do the cube roots on both sides with no issues, right? It's not like doing the square root. Square root gives us issues, cube roots does not. So we can do cube roots on both sides, we get a equals b, which is what we wanted to show. We started with f of a equals f of b. We showed that a equals b, so it must be injective. Okay. Is everyone clear on the calculations? Yep. Sorry, this example here. Yes. Because if I take the square root of 4, what answers do we get? Plus and minus. If I take the cube root of 8, what's the answer? Only 2. That's the difference. So the square root of 4 is plus and minus 2. But if we do the cube roots of 8, it's just one answer. So over here, when we do the square root, we get 2 answers, plus minus. But when we do the cube roots, we get one answer. So a cubed becomes a, not plus minus a, just a. And b cubed becomes b. Okay. The cube root gives us one answer, square root gives us 2 answers. That's the difference. Yeah. Do you see that? Okay. Everyone else see that? Okay. Little homework problem. Like one line. Show that f of x equals 3x plus 2 is injective. Okay. Very simple. We just substitute it in the definition, show that we get a equals b. Okay, it's like 2 lines of working, very easy to do. Okay, any questions on injectivity? Everyone clear? Okay, next, surjectivity. Okay, so this was the first part of an injective function, and then the partner to this is a surjective function. So what is a surjective function? So definition. A surjective function, also called an onto function. Okay, so we have injective is also known as one-to-one. Surjective is also known as onto. And we'll see why it's called onto in a little bit. Is a function, let's say f, such that, now this is a little bit wordy, but please try to follow along, such that for every element in its codomain, not the domain, for every element in its codomain, there is at least one, not one, at least one. There might be two, might be three, might be one, but at least one. At least one element in its domain such that if we call the element in the codomain y and the element in the domain x, like we usually do, such that f of x equals y. So the element in the codomain, I'm going to call that y. Okay, so codomain has element y. And the domain, we call that element x, right? Like we usually use for domain and codomain. Okay, so what does this mean? We're going to look at a very simple picture, one where it is surjective, one where it isn't, and that will give you an idea of why we call it onto. Okay, so picture time. Let's say we have our set x, x1, x2, x3. Three elements in the domain. And we have our set y, y1, y2, y3. For this first example, this is going to be non-surjective. And we can construct it like this. So x1 goes to y1, x2 goes to y1, x3 goes to y3. This is f. Now, we're going to have to keep two things in our minds at once now. So think about the picture and think about the statement we just wrote down. And we're going to check, does the picture match the statement? Okay, so let's read through it very carefully. Okay, so it's a function f. We've got our function. That's all fine. Such that. Now, this must be true. Whatever's after the such that. If it's not true, it is not surjective. If it is true, it is surjective. Okay, such that. For every element in its codomain. For every element in its codomain. Okay, please follow along. Every element in its codomain, there is at least one element in its domain. At least one element in its domain. Such that f of x equals y. Okay, so we go through it again, and then I'll go through the picture. For every element in its codomain, that's these guys over here. Okay, there is at least one. Could be one, could be two, could be three. At least one element in its domain, that's these guys over here. Such that f of x equals f of y. In other words, it maps over. Okay, everyone clear on that? Now we're going to check. For every element in its codomain, we need to go through every element in the codomain and check what? We need to check that there is at least one element that maps to it. Okay, so let's go through the list. There's a finite number of things so we can check. Later on, it's a little bit more difficult. So y1. Is there at least one element that maps to it? In fact, there's two. but it said at least one. So it can be 1, it can be 2, it can be 3. There is at least one. We can pick this one or this one. It maps to it. Y3, is there at least one element that maps to it? There is only one. That's fine. It said at least one. Y2, immediately not surjective. So everyone followed along? Okay. Now we'll draw another picture where it is surjective, and then you can clearly see the difference. So we have x1, x2, x3, y1, y2, y3. So let's say x1 goes to y1. Let's say x2 goes to y3. Let's say x3 goes to y2. We got something like that. And we're going to play the game again. We go through every element in the codomain, and we check that there is at least one, not one, at least one element in the domain that maps to it. Okay, so let's play it again. y1, yes. y2, yep. y3, yes. So it is surjective. Yeah, so that's how we can use the picture to quickly see. But if you want to calculate this to actually see is it surjective or not, we've got another little bit of terminology. Definition. You've never heard of this before, but this is the range of a function. Yeah, you've never heard of it. First time you've heard it, you're hearing it. Okay. The range of a function f is a subset of the codomain. Okay, so we have the codomain. The range is a subset, not just any subset. Such that every element in the range has some element in the codomain that maps to it. Okay, again, so every element in the subset has some, or at least one. Right, you can some elements, at least one element in the domain that maps to it. Okay, now there's a few notations for this. So we can write it as the range of f. We can write it like that. I prefer the following notation. F of x. So inside here, this is just a symbol. It's not f evaluated at x. Inside here, we put the whole set x, the whole domain. So f of the whole set x is equal to all of the elements in the codomain. So all of the elements in the codomain, such that, remember for the set border notation, that was the vertical line, all the elements in the codomain such that there is at least one element in the domain that maps to it. So such that there is at least one x, we should be more specific, x in the domain for which f of x equals y. Yeah. In other words, it is the set of all of the outputs of the function. It's all of these outputs here. So if we go back to our pictures here, we can see when will the function be surjective and when it will be non-surjective. In the first case, we're looking at the range, right? So it's all of the elements y such that there are some elements that map to it. So in this first picture, the codomain is y1, y2, y3. What's the range? Look at the definition. What's the range? Is y1 in the range? Yes. Is y2 in the range? No, there's nothing mapping to it. It's not in the range. Is y3 in the range? So we have this subset, y1, y3, that makes up the range. Y2 is not in the range. Let's look at the second case. Is y1 in the range? Is y2 in the range? Is y3 in the range? All of them are in the range. And that makes it surjective. So we can write an alternate definition. A function f. So instead of doing all of the words, we can just write it in terms of symbols now. A function f from x to y is surjective if f of x, the whole set x, we know that's the range, is equal to the codomain. Please put a big box around this. This is what we're going to be using for the calculations. So a function f from x to y is surjective if the range is equal to the codomain. Yeah. And we'll have a look at one example of this, and then we'll leave it for today. So let's say, example, f from the real numbers to the real numbers, x maps to x squared. Okay. Actually, we're going to do two examples just to show you it's a little bit trickier than you think. Okay, so in this case, we have our domain, we have our codomain. How can we show it's surjective? We calculate the range, we calculate this, and check if they are equal. Okay, so we've got this. Let's calculate the range. Yeah, so it's all of those elements y. Sorry. Where we have x. Yeah, so it's all of the elements y, such that there's some element x where y goes to f of x. Okay, so what happens to the x when we put it into f of x? What do we do to it? What's the rule? How about another 5 points if you answer? Okay, so we put x in, we get x squared out. No one gets the 5 points, sorry. Okay, so you put x in, you get x squared out. What can you tell me about that x squared? You can put any x in, any x from the real numbers, and we get x squared out. What can you tell me about that x squared? Oh, who said that? Positive. Positive, yes, it's positive. So all of the outputs are going to be positive. So what's the range going to be? You said it. The range as a set will then be, it's all of the positive numbers, right? Yeah, look at the picture. We've got y equals x squared. Where's the graph? The graph is up here with all of the positive y values. The graph isn't here where it's negative. The graph is only up here where it's positive. So this is the range. You know the range, right? It's just the y values there. Now the question is this surjective? Does the range equal the codomain? Is this the same as that up there? Yes? Why are you saying yes? Real numbers, all of the real numbers. Are these all of the real numbers? No, they're not the same. These are the positive numbers. That's the range. What's the codomain? All real numbers. So they are not the same. So here we have that the range is not the codomain. This is not surjective. Does everyone see that?
No.
Who says no? Okay, where did we lose you?
No.
This part. Okay. What is the set of all real numbers? As an interval, right? What's the set? Minus infinity to infinity, right? What is this interval? 0 to infinity. Are they the same? No. You put a big line through. They are not the same. Okay, so this is example 1. Example 2, we'll do it very quickly. So we have all the real numbers. But now I'm changing the codomain. I can do that. I can do whatever we want to the domain and the codomain. Is this function surjective? Yes. This function was not surjective, right? We proved that. This function is surjective. I emphasized this last time and I'll emphasize it again. This x squared is not the function. All of this is the function. If I just say y equals x squared and I ask you, is this surjective? You must tell me it is an incomplete question. I did not provide the domain. I did not provide the codomain. I never gave you a function. You see how we changed this codomain from here to here, and it went from being not surjective to now being surjective. That x squared, the rule is exactly the same. Choosing the domain and choosing the codomain is very, very important. Okay, it is not just the rule here. Okay, everyone clear on that? Okay, so we'll leave it at that for today. Remember the quiz next week. So the MCQ, it will be on function domains, like I said earlier. So you'll have some function and then options A, B, C, D. You just pick, whichever one matches up. Even and odd functions, there'll be the definitions, what's even, what's odd. You'll have options A, B, C, D. You just pick whichever one is even, which one's odd. You don't need to take photos. It is on the learn page. Okay. And then injective, surjective, it will be like, here's a function, when is it injective, when is it surjective? Okay. So, like this example over here. So I give you this one and you choose, no, it's not surjective. Right? It's just MCQ, you just pick. And then this one over here, I give you this and you say, yes, it is. Yeah, something like that. Okay, so that's for the MCQ part. And then the written, it will be 2 proofs, 5 marks each. Proof number 1 will be on even and odd functions, something seen or unseen, depending on if you do the homework or not. And then injective and surjective functions, another proof, seen or unseen, depending on if you do the homework or not. Okay, so if you do the tutorial work, you would have seen the answers. If you do not do the tutorial work, then these are unseen proofs. Everyone understand? Big hints as to what's coming up. I hope you understand that. Okay. Any questions? All clear. yeah, I'll see you next week.